Our next set of goals, next set of standards for the semester, relate to what is the actual structure that makes the rational numbers work, right? What are the important properties of the rational numbers that we want to see carry forward when we complete the rationals into the reals? And I use the word complete very carefully here, because maybe one of the most important of the theorems and definitions to know in this section is the so-called axiom of completeness. And this goes back to our mock trial from the beginning of the semester. Right? At our mock trial in the beginning of the semester, we decided that one of the ways of defining what the real numbers were, one of the things that we decided at the mock trial is that one way to define what real numbers are is to define them as the least upper bounds of sets of rational numbers. So I define a set of rational numbers in some way, any way that I like to, right? And as long as that set of rational numbers actually has a finite upper bound, then the smallest of those finite upper bounds is what we call the supremum of that set. And we define that supremum to be a real number, even if that supremum may not have been rational to begin with, as in the example of this set, right? All the rationals whose squares are less than 2 has a least upper bound, but it turns out that that least upper bound is not rational. But by this definition, we can say that it's real. And the axiom of completeness takes that as the definition. So it takes that on faith. It says that every set of real numbers, which is not empty, first of all, and which, second of all, is bounded from above. So the set doesn't trickle all the way out to positive infinity, right? That there is some barrier, some upper barrier beyond which the set does not extend. Right? That this axiom declares that the supremum, the least upper bound of that set, is a real number. So this is where that first definition of the reals that we met during the mock trial comes in. Because we could, if we wanted to, take this axiom and replace the word real here in the beginning, and we could put rational in it, and it would still have the same kind of content. Every set of rational numbers that's non-empty and bounded above has a supremum that is a real number. Whichever way we do it, this is kind of the intellectual content of how we construct the real numbers in goal number 1. And so that requires us to deal with the topic, well, how do upper and lower bounds, minima and maxima, and suprema and infima, so least upper bounds and greatest lower bounds, how do those things work? And then as a secondary consideration, and this is a standard number 1Y, we'll think about the other two principles, the Archimedean Principle and the Inductive Principle. Archimedes is also something that we met during the mock trial. Sort of came out of nowhere, but it's, again, relevant, right? It tells us something about the natural numbers, which are a subset of the rationals, which are a subset of the reals. But one way of stating the Archimedean Principle is to say that the natural numbers go on forever. They have no upper bound. No matter how large a natural number you give me, I can give you one that's bigger. Which seems like an obvious statement if we were familiar with the natural numbers. But it turns out to be this really useful, well, we're going to call it a theorem. Sometimes it's taken as an axiom. But it's this really useful thing that comes up in a lot of unexpected places throughout the semester. It's very often useful for us to be able to assert this from an authoritative perspective, that we can always find a natural number that's bigger. That actually does a lot for us this semester. Let's take one of the rows in this table. So we have 5 different sets. Let me pick one that's got some interesting behavior. Let me choose this one here. Let's choose the second row. So this is the set which is the interval from negative infinity to 4 on the real line, which is obviously doesn't include infinity, but it does include 4. Let me put it on a diagram. Maybe I'll just make it a vertical number line here real quick. So here's 4. And if I'm going to shade this number line to indicate this set, then probably I'm going to put a closed circle at 4. Whoops. So let's go across the column and talk about each of these one at a time. So would we say that -1 is a lower bound for this set, according to the definition of lower bound? For this particular set, there is no lower bound because this set extends all the way down to negative infinity, right? So -1 is not a lower bound, because, so if I want a counterexample how do I know that negative 1 is not a lower bound for the set? Give me an example of something which is less than negative 1, which is in my set.
-2.
Sure, negative 2. Negative 2. Because negative 2 is less than negative 1, and yet negative 2 belongs to my set. Right? So that's my counterexample. That's my one counterexample to this negative 1 being a lower bound. If I turn that around on its head, so what we just... what this shows is that there exists a number, in this case negative 2, but I'm just going to call it x, which belongs to S, such that x is less than my supposed lower bound. Right? Negative 1. Right? So this shows negative 1 is not a lower bound for S. Let's negate that statement. If I negate that statement, it should give me the definition of what it means for something to be a lower bound. Negative 1 in particular, in this case, is a lower bound. So let's negate that statement. What happens if I negate the statement, there exists an x belonging to S? What happens to this quantifier? It changes to a for all. So this becomes for all x in S. And when I negate this conclusion, x is less than negative 1, what does that become? X is greater than, or possibly equal to negative 1. But right, so we turn around that inequality, and there we get it. So now here's the definition that would have to be satisfied if negative 1 were lower bound. Right? If negative 1 were lower bound, that would mean every element of the set S is greater than or equal to negative 1. Right? That seems like a sensible definition for a lower bound. It's a lower bound if every element of the set is greater than or equal to it. Right? There it is in our definitions. Right? That a number m is said to be a lower bound for a set if every element of the set is greater than or equal to that m. Right? So that is the definition of lower bound. So if we want to show that negative 1 is not a lower bound, as we did here, we would just turn around that definition, and all we would need to show is that there exists even just one element of the set which is less than negative 1 to show that negative 1 is not a lower bound. So here we would say no. Right, so negative 1 is not a lower bound for this set. So let's turn our attention to the open interval from 0 to 4. If I diagram that one out. So there, if I'm using my usual interval notation, I would probably put an open circle at 0 and 4. I would connect those two. And that would be maybe how I would diagram this set. Right? Okay. How about this one? Is negative 1 a lower bound for this set? Is it true that for all x in this set, x is greater than or equal to negative 1? Yeah, that's true. Right? Negative 1 is a lower bound because every element of the set is greater than or equal to negative 1. Okay, but then what about this part? Is negative 1 a minimum element of this set? So what do you think is the difference between a minimum and a lower bound? The distinction is that the minimum of a set has to be, well, it is a lower bound, first of all. That's the first thing it needs to be. A minimum has to be a lower bound. So it's a lower bound. But the most important thing about it is it also needs to be an element of the set. So a lower bound that belongs to the set S. So negative 1, is it a minimum of the set? It's not. And the reason it's not is that it doesn't belong to S. Right? It's not actually an element of S. So then let me ask this last question. What do you think the minimum of S is for this set? 0? Is 0, first of all, is 0 a lower bound for this set? Is every element of this set greater than or equal to 0? Yeah, it's a lower bound. But is it the minimum? Why is it not the minimum? It doesn't belong to the set, exactly. So 0 is not the minimum. What is the minimum?
Would you say that it has a minimum, or would you say that it doesn't?
Terrific question, right? So an assertion that we could make about this set is that this set has no minimum. Right? It has no minimum element because no matter what we think the minimum is, it can't be 0, because 0 doesn't belong to the set. It's not going to be anything less than 0, because nothing less than 0 belongs to the set. Could the minimum be anything bigger than 0? Like, let's say I asserted that the minimum was 0.001. Could that be a minimum? It belongs to the set. What's wrong? It's not a lower bound because we can always find something that's smaller, for which we could either make the assertion using the density theorem that we talked about, or we can also do it using the Archimedean principle, it turns out. Right? Because one version, equivalent version of the Archimedean principle is the one we heard about from Team 3 during the mock trial, which is to say not that the natural numbers keep going infinitely, but conversely, take all of their reciprocals. And the reciprocals of all natural numbers accumulate on 0. That's the statement that we heard there. In other words, no matter how close to 0 we get with a small fraction, 0.001, that's 1 over 1,000, right? That because the natural numbers keep going, the denominators of these unit fractions also keep going. And as they do, those unit fractions get smaller and closer to 0. So there exists a unit fraction in this interval. Right? So that's not a lower bound. So there's one way in which the Archimedean principle helps us in unexpected ways.